We have begun. So today, effectively, we start our biochemistry unit. I have a little bit to tidy up on that PowerPoint A, just the last two slides that are there. And this one. It's okay. I used to have that. Everybody be quiet, but now nobody. Everybody ignores me. So when we're talking, these are part of what biochemicals are this catalysts, which basically make equations go in both directions, make things being assembled and disassembled. Your body is governed by these. Indeed, the vast amount of what your genetic code dictates that differs you from one another and makes you similar to one another are enzymes, which are biological catalysts. They're made of proteins. That's why understanding the biochemistry unit is so pivotal to understanding what, and proteins are all about shape and the charges they have and how they fold. And you will see this dramatically in this next chapter. You got the study guide. One of the students in the first class, the 9 o'clock said, could we get my hands on one? Sure. And so you're going to see already, if you see the way the numbers are, and I try to put those on tests, you see this is where it's coming from. A lot of it's going to be in this biochemistry unit, so fair warning. So what happens is the magnificence about them, they can make thousands of reactions go in a fraction of a second because they're unchanged. All they do is either latch on to stuff and let it go, latch on and let it go. And in the meantime, by holding it in the right position, that's where shape comes in, the equation, either something is built or something is disassembled. So that's a big factor. They're influenced by two things more than anything else. Agreed, small things make things happen faster. Yet we need to have a sufficient supply of them. Once you have an excessive amount, there aren't enough spaces and platforms to go it around. So it usually increases the rate, but not always. Temperature is a two-edged sword. As it increases the rate. Once it gets to too high of a point, it begins to break down those proteins in a process we call denaturing. They change their nature, they change their shape. They can't do their job, be it catalysts, the platform, whatever it is. By the same token, the reverse of temperature, if you make it too cool, things are too sluggish, and even then the proteins begin to lose their shape. We're designed elegantly to work around the set point, the homeostasis idea, as long as we're within it with a couple of degrees. 37 is normal in Celsius, 104 temperature, 40. So take 3, you can still function, but you're sick. You take off that 3 degrees and take it to 34 degrees Celsius, all of a sudden now you're like at 92, 93. You're in trouble. Okay. Now, fortunately, we have this. Being colder, there's an ability to reverse that much more so than being too hot. Take a temperature to somebody at 108, we use our regular parlance in Fahrenheit. They're not going to make it. They're going to die. But there's ample evidence of resuscitating people who fell through the ice into the water for 30 or 40 minutes. Because as much as it stops things from happening, it slows things from decomposing. So you always try to resuscitate. If someone there, that you have a shot. And there's so many bits of anecdotal evidence of this. It's very clear. That's the takeoff point for understanding why we're talking about all this stuff. Temperature is really important. The other thing that makes enzymes and catalysts go, pH. Perhaps the major topic for today's discussion as we bring this all into the start of our biochemistry unit. So adios to that. And we take on the other, which is biochemistry. Everything, all the chemicals involved in your body, we classify them in a general way to organic and inorganic, not unimportant and important. Okay, the only thing, the whole carbon thing, and they address this later in this particular PowerPoint sequence, carbon dioxide and carbon monoxide, even though they contain carbon, are considered inorganic. It has to be carbon to carbon covalently bonded with carbon to hydrogen as well. That's what makes it. So carbon and oxygen alone doesn't work. Years ago, we had a thing called carbon tetrachloride, which was a cleaning fluid. We have better ones today. That stuff was so toxic. And we used it so, something spilled on the couch, that type of stuff. Worked great. But if you're inhaling fumes, you're in trouble. That, that was one of with the skull and crossbones on the label from an era long ago. That was in the 50s and early 60s where we saw that. So it was life. It's okay. So they classify into this, and we're going to talk about water and salts, acids and bases, a lot of them. And also there are ones that are organic acids and organic bases as well. Okay, organics, and this is where we're going to start the whole idea. These are the building blocks of life. When we get into this, and they're either classified as small or macromolecules, large. So the first one we address in this, I will touch on it a little bit today, hopefully, are simple carbohydrates. The name we give to carbohydrates is saccharides. So we're going to see, we're going to talk about mono and disaccharides, which means single or double sugars. They are considered small. And then a term you probably have heard before, poly for many, polysaccharides. All this is in the PowerPoints and in text. And that's when we start talking about complex carbohydrates. I'll just do carbs for the time being. And these would be small, and these would typically be considered simple. Because that's a great deal of our energy source comes from them. They're the first one we address. And they also give us an idea of when we start talking about small molecules, generally are single or maybe double units, like these. Talking about polysaccharides, I know where I think it's working. We're talking about the polysaccharides, complex carbs, which the greatest part of our diet is raw. Basically come in three categories. Interestingly, there's just long chains as poly, usually glucose. The way that they're kind of stapled together, bonded together, the way they form structurally, it tells us a couple of things, whether we digest them or not. One that comes from animals is called glycogen. Any animal products we ingest may have this. We have it in really in two places we talked about before that you can store it. That's it. Your liver or skeletal muscle. It's like an emergency energy store. It's very difficult. So we can ingest it and divide and break it down, use it for glucose, we do all the time. The other is starches. Starches are how plants store glucose. And all plants have it. And that's what we derive a tremendous amount we have from starches, whether it's grains, whether we make pasta out of, for example, fruits and vegetables, we have sugar. Typically, vegetables have a fair amount of starches that are associated with them. And all of these, and I'll star those, means we can digest them. We have the enzymes to break apart these chains of glucose, set them free. So, stop talking like that. My pop culture references are from the 70s. And 60s, and even the 50s. I started listening to music with my sister who was older. This was a show called American Dance. Because they danced on the show. That's one of the first media TV shows in Philadelphia. So she could see the dance steps. I like the music. I got into the music. And lastly, what plants have that we can't digest, cellulose. Basically, plant structural material. Plants, cell walls, structural material. We can't digest it, but we can use it. We'll get into all that. We will not get to that today, but it kind of gives you an idea of the building blocks. In this case, glucose is called a monomer, and when we staple it all together, it's called a polymer. So you're going to see a number of examples of that. See my boundless energy today because the Steelers won. They had it the whole time. Fire. What? My wife was tempted to throw a large quantity of water on me after they ended up getting that last play was incomplete. I'm jumping up and down screaming. She advised me to please sit down and be quiet. However, she did not use those terms. It was a little more simple, declarative, and firmly stated, with some additional language to demonstrate her intent. You look like a second word but ends with hole, jumping around. So carbs, fats, proteins, nucleic acids, all are going to classifying this, with the exception of fats or lipids. They don't really have this single unit. It's just they group together naturally, and for that reason, they're very unique in their form, and we'll see that. Moving on, water. What we talked about this endlessly. Water. It's all about those hydrogen bonds. The fact, without going back and looking at the diagram, this very tiny degree of force that holds them, holds those molecules together, accounts for all of these wonderful properties. I mean, even because of that, their attraction to one another, those little molecules are held together. We call that surface tension. Okay, and surface tension is, maybe I shared with you perhaps you're the group that I did. We breathe because of a little bit of water-based material on the wall of our lungs and on the lung itself. As we expand our chest, it creates a little bit of extra help for our lungs to expand. Okay, you'll see this when you get to respiratory. You studied these things already in lab when you talked about the parietal pleura and the visceral pleura. Is that ringing a bell in the pleural cavity? See, there's a reason to learn that. Moisture helps things slide over one another. By the same token, if that little bit of adherence is because it's a very small distance between them. Okay, so that's why it's so important. So there's a whole lot of different properties. Collectively, they have a fancy name. They're called the colligative properties of water. You don't have to know that. But heat capacity, adhetive vaporization, that's temperature. Why you can have 104, 105, 106 temperature and still survive, because it resists, it absorbs that heat by breaking those bonds that can reform when the heat dissipates. And so much so, it's very difficult to vaporize. When someone gets a temperature, they don't start to steam inside. Effectively, what vaporization is, going from a liquid to a gaseous state. So even though some of those water molecules might hop out of solution, it's not like, a boiling water that event, if that would occur, you certainly never survive that. Somebody who was subjected to extreme, caught in a terrible fire, tragic things would occur like that. And then its solvent properties, we already know about that, how easy things dissolve within it. It can separate all of those salts. And the salts are going to play a particular role because that's something that contributes and impacts what a lot of today's discussion is pH, and that centers around water. And as you will see also in this, when we put together those molecules, when we staple those glucoses together, we do so, as you will see in an example in this PowerPoint sequence, we basically take two individual molecules and form a water and pull it aside, and basically leave a bond in its place, that sharing of electrons, covalent bond to join them together. We make a new compound, basically putting the two together to make something else. In this case, two monosaccharides that in this case are different. In the example, they form a disaccharide, also a small molecule, but in the process, we split off of water. So when we make something, we call it synthesis. That's why NTHESIS. When we do so by removing a water. When you remove a water, okay, we dehydrate. So dehydration synthesis is how every time we make a chemical bond, we do it in the body by way of organic molecules. Dehydration synthesis. Flip side. So you did a carbohydrate load. My wife had, pasta and sauce last night. I had a burger. Okay, so what? That pasta is a complex carbohydrate. How did you break it down into its basically component of glucose? You added water. The water separated that bond, effectively broke it. We lysed it, Lysis. Lysis is destroying something. It did so with the aid of water, hydrolysis. So you could say hydrolysis or hydrolysis, but that's how it's spelled, all one word. You'll see that here as well. So water plays that role. and cushioning. The example they use here is the example everybody who teaches A&P does, is cerebrospinal fluid, which is mostly water with a different sort of constituency of electrolytes and stuff in it. Okay? Similar to your blood plasma, not the same. We talk about that toward the end of the class. If you didn't know it, your brain and spinal cord originally were matter, organized matter around a tube of fluid. And as that tube expanded, enlarged, folded, still in the center of it is fluid. And what happens is there's ways for that fluid to escape. So it's got fluid in the interior and fluid on the exterior, the cerebrospinal fluids in both places. Effectively, that cushions it. It also gives it buoyancy. So your brain and spinal cord are actually floating because of the fluid within lowering its density and the fluid without keeping it floating. So that way, when you're doing a sport, jumping up and down like those guys on the football field or the gals playing basketball, I think they played Sunday, the Fever, I think qualified for the playoffs, no Caitlin Clark, whatever, trying to cover men's and women's sports equal. It wasn't smacking them around. That's how when you get a concussion. Basically, the impact is so severe, it overwhelms the cushioning. And if you hit it from here, the part of your brain on the other side strikes there. You always look on the opposite side from the trauma when you're looking at it in a scan or something like that. Little hint. All good? That's the buoyancy that it provides. So the fluid is everywhere. There are places where you can lose that fluid. It can drain out. My wife's best friend had a lumbar puncture or spinal centesis, basically a spinal tap. It was a bad back injury, and they wanted to see if she needed surgery. It never healed. It constantly leaked, and literally her brain started to sink down into her skull. And it's a fancy name called spinal hypotension. It loses pressure, and it's life-changingly painful. Can't balance, can't do anything. She can barely get out of the house. A wonderful person. They've been best friends for 4 years. And now she sees her occasionally. They talk every night, on FaceTime. So very hard for her to get out of the house. Just saying. You'll learn a little bit about that again, and I'll probably reiterate that same story that's there. So it's just, these are things that occur in real life, and it's a unfortunate thing. Fortunate for you, unfortunate for me, is that as you get older, you become more acquainted with these kinds of things that different folks in your orbit have. So here's the heat capacity: absorb and release, prevent sudden changes, vaporization, requires a large amount of heat. So useful cooling mechanism, so it can tolerate that heat without all of a sudden with the liquid still staying there. So it's really very, very useful. We dissipate heat the same way in our skin with perspiration. Okay, as it evaporates, absorbing that heat, then it cools, then it can get out. And that's a cooling mechanism. So one of the great things about perspiration or sweating, and there's a subtle difference which you get to in skin. Did Dr. Robbins talk about insensible and sensible perspiration? Yes? No? Yeah, that's nothing you would ask students at this level. We lose it. Even if you don't perspire, you lose a certain amount of fluid every day through perspiration you can't even feel. If you're somebody like me, I go out and walk the dog, I'm sweating. The dog's fine. I don't want to go in. You're going in. You try to tell a 74-pound dog he has to go in. I'm not done yet. We'll finish up. Doofus. So dissolves, disassociates, ions, important. We're getting to it. Even proteins, as big as they have, most of the time they have areas that have positive charge and where they have no charge at all. So they have a bigger part. They have polarity in the sense that they have either positive or negative charge, where they can dissolve in water, yet they have areas often centrally, which is uncharged. Why they can fit in membranes and move around. Okay. Surprise you, why does this giant molecule called the protein not disrupt the cell membrane? It can move around it. It's very, very interesting because of that. And that's where, and here you can see the example where it surrounds. We did enough time on that. Here's the hydrolysis and dehydration synthesis. Here's the cushioning, cerebrospinal fluid, blah, blah, blah. We've talked about salts. They dissociate into separate ions in water. Okay, either positive or negatively charged. So when we talk about sodium chloride in water, salt in water, it's going to form sodium with a plus sign and chloride with a negative sign. You'll see that. Sure. Why it didn't include this is a topic that we call heat. Okay, here's good old water molecule. Remember what made it sort of unique, made those neat little hydrogen bonds that were there. These electrons were being pulled closer, effectively, to the oxygen. It's like an intramolecular tug of war. Like any tug of war, it doesn't stay static. Very so often, a very tiny amount of these molecules become different because they effectively, oxygen wins the tug. What happens is that electron gets pulled over here. Now oxygen becomes O with a minus sign, and the whole molecule becomes OH, the minus sign, called the hydroxyl ion. What's left over here is a hydrogen all by itself. All it has is a positive charge because it lost its electron. We call that a proton, or we can just call it a hydrogen ion. Again, those names are interchangeable. To note that. In tests, you might see the word proton or hydrogen ion. No excuse for not knowing that. So you can fool students who haven't been listening. That's what a lot of people do, including. So we got that. It doesn't happen a lot. Indeed, by and large, water is not all of it splits apart. To be very accurate, water stays by only a tiny amount. How little, Dr. Stein? Funny if you ask that. If you had 1 times 10 to the negative 7, then we have a negative exponent, not a negative number. 1 in every 10 million. So if you had 10 million water molecules, one of them would break apart. 1 out of 10 million. Why do I care about that? You might be saying to yourself, but here, that's where this guy comes in. And half a tablespoon of water, slightly maybe a smidgen more, we have a mole of water, 6.02 times 10 to the 23rd. And when you want to figure out how many of these actually split numerically, not by some esoteric, scientific notation, you multiply. 1 times 10 to the negative 7 times, brackets, order of operations, 6.02 times 10 to the 23rd. What you do when you multiply scientific notation, you guys should already know this, you end up with, you add exponents, subtract in this case, you end up with 6.02 times 10 to the 16th of positive charge. Frankly, an equal amount of negative charges because it's electrolytically balanced. It always goes, those exponents always add up to 14. It's an amazing number. That's 6 times 1,000 times a trillion. That's a significant amount of charges. That's why typical water that you get out of the tap that hasn't undergone complete deionization, which we do in the laboratory to get like triple distilled, what's called deionized water for certain experiments, that will, you have an apparatus in a lot of little chemistry or biology classes, you'll stick it into tap water from a beaker and a light bulb will light up. That's all those charged particles. That's the importance of those charged particles. The number is minute if you think of it in scientific notation, but in a molecular sense, tablespoon has a ton of charge. That's why this is significant. And anything we add to that water will impact it. By and large, simple things like a pinch of table salt probably isn't going to make a bit of a difference. So when we find out what is this pH, we look in chemistry, or in chemistry class, like some of the folks here are taking this sort of thing. I'll talk about pH and pOH. Okay, for our purposes, but more of that. pH, by definition, is the percent of hydrogen ions. So we're only interested in that number, the 7 after the negative sign. It's called the negative anti-logarithm. Worry about that. All it means, you look at the number after the negative sign of the hydrogen, and to figure that out, so if we added something that's going to make it acidic, let's say it's going to make that 10 to the minus 5. As that exponent goes down, the other side would be 10 to the negative 9. This is where the confusion starts. By lowering, in other words, as pH lowers, acidity increases. That doesn't make any sense, except when you can understand it's a negative exponent. So if that was 10 million, was 10 to the minus 100,000, it's 10 to the minus 5. 1 over 100,000. That's 100 times different. It makes effectively the value of this fraction 100 times greater. When you make the denominator smaller, this is the numerator. You had that like 1/2 over 1/4 compared to which is bigger. Do I want a half a pizza or a quarter of a pizza? I want the half. Bigger. Smaller denominator, so increases the overall value. If you can use my favorite, the just because rule, just because I said so. The pH is more acid, it means the pH went down. If you hold that, the opposite is true. Okay? So we're at that place. So that's why the distinction between positive and negative ions, why they're not there. So when we dissolve something, they can conduct electrical currents, as I was describing it. They're vitally important, these charged particles. Nerves and muscles couldn't function. Your heart, if they're doctors go ballistic when potassium levels and calcium levels are irregular. There's a very narrow range for normal. You want to see somebody get excited when they see a blood test like that? Tell somebody that their potassium is low. They're going to be starting IVs and sticking potassium in people ultra fast. So it's all about homeostasis. Sodium chloride, because the big players that we're going to see in the next chapter about the cell that maintain basically something we call the resting membrane potential. That keeps the cell intact and allows it to function properly. Okay? And normally it doesn't change except in nerve and muscle cells, but it's important that it stays that way. There's always more sodium outside the cell, more potassium inside the cell. Okay? Well, to maintain that environment properly, it involves sodium, calcium, potassium, chloride, variety of proteins, all of these things. So they're important for that, sodium chloride and potassium chloride. Calcium, this is calcium carbonate and calcium phosphate, are all about calcium and bone. And phosphates play a big role also within our body. Remember those CHON, okay, CHON and then calcium and phosphate being the big players that we have in our bodies. So all of those, but when you add a lot of these salts to water, they change the pH just enough. So our blood's pH is relatively neutral, but not absolutely neutral. Absolutely neutral is 7, equal amounts of H pluses and OH minuses. Ours is in a range of 7.35 to 7.45. So if you saw that number or someone just said 7.4, they're both correct. So we have a certain, like I said, very little absolutes. There's always a little bit of range. If you go below 7.35, big trouble. Above, big trouble. It's acidosis or alkalosis. It's very, diabetic, that's going to put you in the hospital, maybe in ICU. Okay, so that's the kind of thing we look at. Why is ours not that way? Because if you add all the salts, the mineral content tends to be somewhat alkaline. If you're like our house, we have like a Brita filter or a Pure, a couple of those things, the pitchers, run the water through it like I did this morning. Effectively, they're acidifying the water. They're doing that by removing some of the minerals. When you remove the minerals, it becomes a little more acidic, and that tastes a little better to us. When we move a tiny amount, it actually makes the water taste better, sweeter, acidifying the water. Not that we're adding sugar to it, but that's kind of how those work. It's a neat thing that the chemists are familiar with called an ion exchange resin column. Back years ago, we had things called water softeners. Some houses still use them. It's been around for a long time. Effectively, this is a system that we utilize. And most people use those systems, depending on, because the city water has so much stuff in it to make it safe to drink. Sometimes it doesn't taste really good. Maybe you're lucky where you live and it tastes really good. So acids and bases are electrolytes. So what makes them an acid or a base, when you put anything into water, does it make more hydrogen ions available or does it take them away? That's the definition of an acid. It basically, they call it proton donors. They release hydrogen ions. They don't have to be made like hydrochloric acid with protons. They just have to make more of them come out of what they're dissolved in, the water. So that's a better way to express it. Hydrochloric acid is so acidic that every little hydrogen is released immediately. And the fact that it's all that is released and released quickly makes it a very strong acid. That's why it has a pH that's effectively 0. The hydrochloric acid is the foundation of how our stomachs help to break down our foods, kill bacteria, and start the process of protein digestion. That pH of that hydrochloric acid with the other stuff that's in your stomach, the liquid in your stomach, is about a pH of 2. That's why if you've ever thrown up and you get that, oh my God, it's burning, that type of stuff that you feel in your mouth and in your throat, that's the acidity. When people have reflux disease, that's that acidity coming up in an area that can't tolerate it. It burns. Makes ulcerations in the esophagus. They are very nasty. Okay. So all this stuff that you hear about, you get the digestive, what they now use the acronym GERD, gastroesophageal reflux disease, heartburn, agita, whatever name that you use in your orbit, in your family. Everybody has a different way of expressing it. So that is hydrochloric acid, something that's a little less, but we use it all the time, but we consume it. Acetic acid, another name for that is vinegar. We use it all the time. Our body uses it all the time. You're going to learn the most important neurotransmitter is called acetylcholine. The acetyl group comes from acetic acid, so we're constantly making it and using it up. Okay, its pH is about 5-ish. So, okay, and here's carbonic acid. I'm going to diagram that in a second. That's a mixture of two things, and it's the most important, I think, of all when we talk about acids, because it's weak. This is super strong. This is relatively strong. This is a weak acid, which you're going to see when we talk about buffers. So how is it that when you and I consume coffee, when you a cola drink, if this was cola, if this was a Coke or a Pepsi, diet or otherwise, doesn't matter, okay? Or if you're consuming coffee or chocolate or milk, okay, or sprinkling lemon juice on something, how is it that all of a sudden, it's how are we able to deal with that and not have massive changes inside in our pH? That's because of buffers. We will get to that very, very shortly. So bases, just the opposite. They'll take those extra protons and take them in. Okay. So because they're always relative, if one goes up, the other goes down. If one goes down, the other goes up. It creates more proportionally of hydroxyl ions. And here's bicarbonate, a very important base. When you hear about someone getting sodium in the old days, they took sodium bicarbonate, dissolved it in water, and that was the way if you had heartburn or something like that. You didn't go get a Tums or Rolaids or whatever. Okay, totally different. And ammonia, something unfortunately we make a lot of, and down the road you're going to see that's another way that our friend carbon dioxide works for us. It's a very versatile molecule, even though it's inorganic. And here's the pH scale. We're getting pretty close to where we start talking about this in greater detail. Concentration of hydrogen ions, the more we have of them, negative logarithm, just look at the last number. The brackets are concentration, blah, 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 blah. And this is, and again, you can read through this. This is 7 is neutral. Again, our bloodstream, our plasma, 7.35. It gives you an idea. Why acidity tastes good. We use it. In cooking, you have salt, sour, sweet, and bitter. Sour is acidity. You make something in cooking, you want to touch those buttons. You want something that's salty, you get a little bit of salt. You add lemon, squeeze lemon juice on it. It brightens the flavor. Think of all the dishes we do that with. Okay, you want things that have a certain sweetness. Even some things are bitter. I mean, if you like romaine lettuce in a Caesar salad, there's a certain bitterness to that. Arugula, another ingredient. So all those combinations, that's what chefs do. When people, and good family cooks, home cooks do, they take all those things into consideration. So if you like coffee, pH 5. Oh, it's a little too acidic. We add dairy to it. It's still acidic on the scale. Wine. Some of the bite. When you have very dry wine, it's much more acidic. Sweet wines are less acidic. Here's the lemon juice. pH 2, gastric juice, stomach contents. Here's hydrochloric acid. Oh boy. And look at how bad it is on the other side of that. I mean, egg white, okay, we could consume that, but over here, household bleach and ammonia, oh, that's when people want to do themselves in. That's nuts. I mean, that just tears everything apart. There's no coming back from that. That's corrosive. A lot of medicines, bless you, taste bitter by intent, because you don't want some little kid grabbing pills that have opened up from mom and dad or grandpa and grandma and start playing, and spit them out. So there's a certain intent to incorporate a little bit of bitterness. And this just doesn't make, I don't care. Yeah, you did this in high school. You had sodium hydroxide, hydrochloric acid, and you end up boiling out the water and you left salt on the bottom. This is the big equation. What buffers do is they're able, because weak acids make good buffers because they're willing to either donate or accept a proton. So here you take your two waste products. Most of the carbon dioxide isn't in a gaseous form. 70% of it's in your bloodstream. Okay, it dissolves in the water. It mixes with water of your bloodstream in the presence of an enzyme that you don't have to know yet. It's in your blood called carbonic anhydrase, and it's reversible. And that's the beauty of it, how you can expel the carbon dioxide in your lungs. It makes this, which is called carbonicated acid, H2CO3. That is a weak acid. What does that mean? Weak means it holds on, it stays assembled. It only ionizes a little bit, typically. And it ionizes into the good old-fashioned proton or hydrogen ion and HCO3 minus, which you call bicarbonate. Again, that sodium bicarbonate is a mixture of those things. And you have it, that Arm & Hammer thing in your refrigerator so it doesn't smell. Little box. You know what I'm talking about. That's the beauty of it. Weak acids make great buffers. Because if a proton comes along, yeah, I can take care of the proton. I got a home for it. If a base comes along, yeah, I got protons to give. So it'll donate a proton or not. Strong acids, here are my protons. I don't want to see them ever again. They're never coming back. Out. Here, hey, we can take them or leave them. It's a very, pardon the term, ambivalent molecule. I can take them or I can get rid of them, but I'm here, we're good like that. Voila. Buffers. Calcium in your bloodstream, also a buffer. Proteins in your bloodstream, also a buffer. By far and away, the most important buffer. You're going to see this. Why am I spending all this inordinate time on that? You're going to see this again. You're going to see this in cardiovascular. You're going to see this in blood. You're going to see this in respiratory. You're going to see this in kidney. It's everywhere. It's how we make the acid in your digestive system. It's all AP2. It's how we expel the carbon dioxide in respiratory. How we adjust the pH in the kidney. Because irregularities in pH, those aforementioned proteins start to denature. Not as badly as high temperature, but they start to break things down. That's why diabetic acidosis is a big deal. All of a sudden, the proteins that govern their body systems don't work. So, very narrow pH range. Before we had those neat little things you could stick on the finger, okay, you couldn't get a read based on arterial blood gases. You couldn't tell whether they had a blood O2 sat of 98 or 96, which is really good, or 82, they're in big trouble type of thing. We had to do what was called arterial sticks. They'd come in the emergency room, typically the burn, when I learned to do it. And you'd be taking blood out of the radial artery. Not easy. Because that thing's moving around. And then we sent them to the lab. It took a half an hour to find out, what the person's blood gas is. In the meantime, you got to sort of treat them accordingly, what you think might be there. We didn't have that instant appreciation. Oh, their pulse ox is good. We've got a little wiggle room here. You'll learn in blood it's a slippery slope. Once that baby starts to go down, it's like you're on a water slide. Oh, no coming back. Moving on. So here's the organic molecules. It's electrically neutral. Never is the wrong word to use here. It does sometimes. gain or lose items. We can do that in the laboratory. Ordinarily, it shares. We did the covalent bonds, unique to living systems. Here are the ones that we're going to look at how the building blocks get built, early days here. And that's what I want. That's why I wrote that. So we're getting to that point. We look at effectively the building block, which is called a monomer. Mono means single, mer means the unit. Okay. And again, we're going to look like glucose up there is the monomer. And those other things, the glycogen, the cellulose, the starch, are polymers. We have identical, in the case of glucose, or similar, structurally more or less identical in the case of things we're going to learn about called amino acids. There's 20 of them. They're all different, but they're structurally similar, so we can use them to make different proteins by just taking a different one. They could all be the same. They could all be different. You have effectively an unlimited amount of proteins you could assemble in your body. Not that you do. We have a pretty good idea of the ones you assemble, but we know the variations. So carbohydrates, again, the oddball here that doesn't follow monomer polymer are lipids or fats. Again, they're individual units whose properties make them have a tendency to cling together, but they are separable. They're separable. Proteins are made of amino. We're going to get to all of this. I know I'm going fast. And nucleic acids are made of something called nucleotides. And we'll see why. So here's the whole polymers. And again, dehydration synthesis, take away water. Some authors, maybe the one in Welsh Hall calls it condensation, like the water you had on your windshield this morning, on the glass of your dormitory on the outside. They have windows in the dorms, I take it. It's not jail. The last dormitory I was in, the room was so freaking small. My son, the one in the picture, he started in 2005 at Duquesne in either St. Anne's or I was at St. Anne's. The room, I don't know how two people could walk in the room. I mean, you had the two beds, you had to go sideways to get between the beds. So the guys, they stacked the beds and somehow managed to get a couch in here. You know, creativity. It's the smallest freaking room I've ever seen. But when you have a Navy guy and a Marine, yeah, we get it done. Broken down by hydrolysis reaction. Everybody's picking up. We have 7 minutes. Here's the hydrolysis. Voila. Okay. So here's the aforementioned, these OH groups. All of these molecules have them. And so if you take away the water, you create a bond. Store energy. You can reverse it by adding water and breaking them apart. Classic example. Here is glucose. Here is fructose. If you did not know it, our brain only works on glucose. Sperm, for instance, only work on fructose as an energy source. Okay, so there are different sugars that we use. By far and away, I'm fond of saying all roads lead to glucose. And here, when you combine the two of them, you get table sugar, sucrose. Whether it's in a little packet, in a sugar cube, however you have it, or it's in a big thing that's used for cooking or baking that you might be using with at home. So that's sucrose. Glucose and fructose make sucrose. So when we put it in water and you have an enzyme, that enzyme will break it back down and your body can change it. When we absorb it, basically it's glucose. If we have to make fructose out of it, say for sperm cells to be activated, no problem. Those are monosaccharides. So carbohydrates, equal parts, we did this before, carbon and water, 2-to-1 ratio. Single, two, and poly for many. Here's that formula again, CH2O. So carbon and hydrogen and water in equal parts with an N, general formula. The big players. Okay, we do use 3 carbon sugars and even 7 carbon sugars. We'll touch on the 3s, we won't touch on the 7s. Our ones with 5, ribose and deoxyribose, RNA and DNA. The difference is they're missing an oxygen. Yet one is a linear molecule and the other one is that wonderful twisted ladder that we'll spend time with. And hexose, 6 carbon sugars versus pentose, 5 carbon. Here's the difference right there. There's the O. Here it's not. Take away an oxygen, changes everything. And here's the 3 monosaccharides. All of these together, as we'll learn next time, make different sugars that we use routinely. Glucose, fructose, and galactose. We can interchange all of them, even though their shapes are a little bit, even though this is more of a pentagon and these are hexagons. Here you can see carbon groups hanging off 2 of them here, only 1 here. I'll leave you with that. We'll start with disaccharides next time. Thank you very much. Remember, not here Friday. Likely you will get a recorded lecture. You can email me with questions on the study guide or things like that, including Friday or over the weekend if you start to study. I don't know how fast I'll get back to you. It depends on when I can get a signal. Whereas my wife and I have to go some distance.